Hello, my name is Jim Meadows, and we're going to spend some time together going over the differences between the 1994 version of the Y14.5 standard and the 2009 version, which has just recently come out. The book that we'll be using is this one on the screen and in my hands. This is about 165 pages of material. In the first portion of this book, there is all of the changes that we're going to go over, and in the second portion there's a workbook, and in the last portion there's an answer book. And to be honest with you, that's not exactly the last portion. There is just about 5 pages beyond that, 5 pages of reference material, some of the things that we'll be using in this course but aren't necessarily new to the Y14.5 standard. This is what I do and have done for many years now. I've trained about 50,000 people in geometric tolerancing and related topics. And I've written 12 books on this topic, and I'm on 12 ANSI and ISO committees. ASME sponsored many of these committees, and most of them deal with either dimensioning and tolerancing practices, the measurement of dimensioning and tolerancing, or gauges and fixtures. I'm the chairman of the Y1443 standard on that. I don't want you to get the impression that this is a complete geometric dimensioning and tolerancing course. This is just the new stuff. The complete geometric dimensioning and tolerancing course is actually taught out of a much thicker book. This textbook was also written to explain all of the dimensioning and tolerancing practices, including the ones that are in the new 2009 Y14.5 standard. But it goes into all of the things that were in prior standards and also how to apply that material. So instead of using this 600-page book, we're going to use this 165-page book and just deal with the new stuff. Now, to begin with, we'll take a look at the material that is new symbology. There are quite a few new symbols, and I've got several of them here. We have a translation symbol, and most of these symbols will be dealt with in later pages in this textbook, but what I'll do here is just introduce them, and then later on we'll show how they're used. We have some very complicated new concepts that are called material condition boundaries. The truth is that the concepts themselves are not new, but the way we speak about them is new, and how we've refined their understanding is new. So this symbol, which everyone knows as the maximum material condition symbol, still means maximum material condition if used after a geometric tolerance. But if it's used after a datum feature, it means maximum material boundary. Now, maximum material boundary is going to need some explaining, but essentially what it is the applicable virtual condition boundary. And of course, what we'll have to do is show how to calculate that applicable virtual condition boundary, which is one of the hardest things to learn in geometric tolerancing. Now, let's talk about overriding certain spatial degrees of freedom. Page 39 shows that we can put datum features in the feature control frame and then say what spatial degrees of freedom they would commonly, or that they would in this instance, eliminate, and we can override some things. The way to think about this is fixturing. And again, fixturing being the physical embodiment of the theory. Let's say that our part, which is of course not like this, but let's pretend that it is, we lay it down on the A datum, which is the underside of the part. Now, of course, what that means is that that A datum eliminates certain spatial degrees of freedom. In each of these controls, it shows what that degree of freedom, those degrees of freedom are. Z, of course, means that it can't move this way. That's a linear degree of freedom. And U, which is rotation in one of these planes, and V being rotation in the other. Remember that when we're talking about this, we're talking about that we have the X, Y, and Z on the drawing, and these are representative of the axes, and U is what rotates around X, V rotates around Y, and W rotates around Z. So if we lay it on A, what it says is it controls Z, U, and V as far as its linear and rotational degrees of freedom. All that really means is that this part can't move up and down, it can't rotate this way, and it can't rotate this way. A commonly does that, and it's allowing it to do it in this case. In this control it says if we stuck a pin into the square hole, and we said that square hole was our secondary datum feature, that commonly the datum feature simulator that fits into that, a square peg in a square hole, for example, if I stuck a square peg in that hole, that would eliminate everything else that the part could do. It could not move in the X and Y fashion. And notice there is an X and Y after the B, saying that B controls the movement in the X and Y directions. It does. This is not new. But what is new is the last rotational degree of freedom, which is W, which would be in this direction. And on the table, be like this. If I stuck a square peg into one of these holes that was square, it couldn't rotate like this. A square peg would stop it from rotating. But this says only X and Y are controlled. That's only movement this way and this way. And it's not controlling rotation. This is overriding it, because here, when we call out things to A, B, and C, C is unnecessary normally. But since we're not allowing B to control the rotation around the Z-axis, which would be W, we're saying that C would control that. So on this drawing, if I just step away a little bit, we can see that C is this round hole. Now think about it in terms of setups. We lay the part down on A, and that stabilizes it some. We stick a square pin in a square hole that represents B. That part can't move at all. But this is saying that it can. It's saying that it can still rotate. It can still rotate like this. And that's why this C datum is called out and referenced in this control. It's saying that these holes, for their rotational aspect, are controlled by this hole. So these two holes can't rotate, and this is what stops it. Now, how would we do that? Well, I guess in fixturing, what we could do is we could create a fixture that had a square pin that went into this hole, in its base was round, and its base went into a round hole on the fixture. And what that would mean is the part couldn't move left and right because there's a pin in this hole. But because this square pin can rotate, that the part could still rotate. And then we would have that W degree of rotational freedom that C could stop. It would be left over. And then we could stick a pin in the C hole, and it would stop the rotation.